Okay, all right. Well, it's Friday. Happy Friday. And I hope you guys are doing well. I have posted under week 3, I've posted homework number 2. I know you guys just turned in homework 1, but homework 2 has been posted, and it is due a week from Monday. And I think that's also, I'll double check, but I think we have our first exam scheduled for that day. So it's like due the same day as the exam. And I know that's like, people don't like that. But at the same time, I do think you should do the homework, and that will help you study for the exam too. So, I mean, there's a little bit of a balancing there. And, but yeah, we'll talk about the exam next week. As time just keeps ticking away. All right. Okay. Today we are going to talk about importance sampling. Okay. So this week we've looked at Monte Carlo integration. Monte Carlo integration is all about getting an estimate of some kind of integral, or some kind of quantity. We have to kind of be able to express what we're interested in the form of a function times a PDF. Function times a PDF, and if we want to get the value of that, we can just kind of sample values from that random probability distribution, and then take the average and get a quantity there. All right, so we have something called importance sampling. Now, I don't like this name, importance sampling, but this is just what it's called. I think a better name for this technique that we're going to learn, I think a better name would be like weighted Monte Carlo integration, okay? Because we've covered Monte Carlo integration, and in my opinion, this is the same thing as Monte Carlo integration, but you just include like a weight factor, okay? So I would call it weighted Monte Carlo integration, but it's known as importance sampling, which is fine. But just later on, we learn actual sampling methods, and those sampling methods are used to generate samples of points. And so in my opinion, it makes sense to call those methods sampling methods. And this one, importance sampling, doesn't actually generate a sample of points. So I'm not sure why we call it importance sampling, but anyway, that's just my my opinion here. Okay, so all right, so here's a review of Monte Carlo integration. We are saying we want the expected value of the function h applied to the random variable x, where the random variable x has the PDF f. Okay, and that can be expressed. The formal value of this, the official value of this, is the integral of h of x times the PDF f of x, okay, across all of the possible values of x in the support of x, okay? And we can estimate this quantity, this expected value, or this integral, by just drawing random values of x, okay, x sub j, a whole bunch of them, from our random distribution, and then taking the average of all of those things. So this is our Monte Carlo estimator, and it requires us to be able to produce random values or random samples from this PDF f of x. Okay, and so far the f of x, the PDFs that we've seen, were like the uniform distribution on some closed interval, and we can generate values from there. And then the other was we did one with the normal distribution, and we said, the computer has this function called rnorm, and it's able to generate random normal values. Later on, so next week, we will learn how to generate random values ourselves. But right now, we're going to just say the computer is able to generate random values for us. Okay? But we do have this question: what do we do if we can't generate random values from f of x, okay? Is there anything we can do? Because all of our methods require us to generate random values from f of x. What do we do if we can't? If we can't generate this from f of x, okay? Yeah, this is what we have. So I said currently what we're doing is we're generating random values using R's built-in random functions, okay? And so R has a whole bunch of these functions, and so we can do RUnif to generate uniform. We can do RNorm to generate random normal, RBeta to generate random values from the beta distribution. You know, there's the gamma, exponential, chi-squared, F, Poisson, binomial. I don't know, you had to learn a whole bunch of these different probability distributions in what, 100B, I think? And so, you know, you learned about all of these things, and R has a lot of these functions built in, and you can just say, hey, give me random whatever, random Poisson, give me random gamma, give me random this and that, and we can do that. Okay, so the question is, what if we can't generate values from F directly? And then so what we're going to see next week is we will talk about how to generate random values from different distributions. So you might be given a distribution that doesn't fit one of these, you know, named distributions that you learned about. Okay, so there might be some other distribution with a totally different PDF or something, and we don't have a function built in. And so next week we'll talk about, okay, what can we do to solve that, right? But for today, we will perform importance sampling. So importance sampling is a way for us to kind of still estimate this quantity that we want to get, even if we can't generate values. So again, this is what we want to do. The problem is we can't generate values from f of x. So what we do is we're going to just generate values from a function that we can generate values from, okay? So we're going to say, well, I am not able to generate random values from f of x, but I am able to generate random values from g of x, okay? So I just says we instead choose to generate values from an entirely different distribution. As the word entirely different may not be perhaps isn't the best thing. Okay, we'll just say from a different distribution, g of x. Okay, it can't theoretically, it could be almost entirely different, but in general, it's better if g of x and f of x are similar to each other. But you know, mathematically, it really can be in something entirely different. Okay, you do have one requirement, all right, and that is the entire support of f has to be within the support of G, okay? So that means if there's any spot where the PDF of F is not 0, then the PDF of G also has to be non-zero, okay? So, so you're just not allowed to have G be 0 where F isn't 0, okay? So for example, if your PDF is the normal distribution, the support of f is negative infinity to positive infinity, okay? And so whatever g you pick also has to have a support that goes from negative infinity to positive infinity, okay? On the other hand, if your f is, say, the beta distribution, then your support is just from 0 to 1, okay? And then so you could choose any PDF, really, that has at least something between 0 and 1, okay? And it could be going from negative infinity to positive infinity. That's fine. It's a little wasteful, but you just need to make sure that the support of f is entirely within the support of g, okay? All right, and all we do is we just multiply by g of x over g of x, okay? So we said, well, the expected value of h applied to x, where x is a random variable coming from f, is found by equal to the integral across the support of x of h of x times f of x, and we're going to just multiply this by g of x over g of x, okay? And then g of x itself is a PDF, right? So now we're going to just kind of group these things together. H of x times f of x divided by g of x, okay? This quantity right here. So this is in the function of some function, some arbitrary function h of x times some PDF f of x, okay? And this is also in the form of some arbitrary function. We can call this k, all right? Some arbitrary function times a PDF, okay? So here we have function times a PDF, h of x times f of x. Now I just have a more complicated function times a PDF. So it's still in the same form. So if the integral of this evaluates to basically the expected value of the function, okay, this whole thing also will integrate to the expected value of this function, okay? So now the expected value of h applied to the random variable x, where x comes from a PDF f, is now equal to the expected value of this function, h of x times f of x divided by g of x, applied to the random variable x. But this time, the random variable x comes from a PDF g. Okay? So we have a different PDF here. Okay, and so you could see why we're not allowed to have that the supportive f has to be within the supportive g, okay? Because if we ever have a situation where f is non-zero and g is 0, then we run into a problem because we're dividing by 0. But if everywhere, okay, so if there's any location where x, if we're going outside of the support of x, okay, then f of x is just going to be 0, so we don't have to worry about it, okay? So the entire support of x isn't contained within the entire support of g, so this is going to be something that we can evaluate for all values of x inside the support of x. Okay, and that's it. That's important sampling, is we just we change the random PDF, the PDF that we're going to use to generate our random variables from f of x to g of x, and then instead we calculate a different function. Okay, we're going to have h applied to x, but we're going to multiply it basically by this weighting term, f of x divided by g of x. Okay, let me pause there for a second, and I will give you your first view quiz answer, which is the letter E. E as in elephant. Your view quiz answer number 1. Okay, so the process, the steps are as this. We are going to generate random so again, the idea is, our goal is we want to get the expected value of h of x, okay, h applied to x, where x is a random variable coming from f, but we're not generating values from f directly. For whatever reason, we can't do that. So this is what we do. We generate values from g of x instead, a different distribution. And then we have to calculate h times f over g. So we apply the function h and f and g to each of the values that we sample, okay, and we compute this quantity, h of x times f of x divided by g of x, okay, and then we do this for all of the different values we sample, and then we take the average, okay, and that average value is going to be equivalent to this estimated, well, not equivalent, but it'll be an estimator of this thing, okay, the expected value of h of x, where x comes from f. Okay, so basically how this works is we're drawing random values from g, but we want to estimate the expected value of function as if they were drawn from f. And important sampling works because basically any value that we draw from g is going to get reweighted by f of x divided by g of x, okay? So here I'm going to have two distributions, and this is kind of silly, but we're going to have F is a beta distribution with shape parameters 2 and 4, and G is a beta distribution with shape parameters 5 and 3, okay? And we're going to pretend that somehow my computer is only able to draw values from G of X, but not F of X, okay? Because that's the point of this thing, is that we're able to generate values from G of X, but not F of X. So what do we do, okay? So F of X looks like this in blue, and G of X looks like this in red, okay? So both of them have a support going from 0 to 1, but the shape of their things is different, okay? And so what's going to happen is the true expected value, okay, the expected value where X comes from F, we're going to draw a whole bunch of values. We should be drawing a whole bunch of values near point 2 and not very many values around, 0.7 or, like 0.8, okay, in blue, okay? But then when we generate our random values, we're going to get our red distribution is going to generate a whole bunch of values near 0.7, okay? And not really that many values around 0.2. So what we're going to do is we're going to compensate, and we're going to say, okay, every time you see something like 0.7, we're going to kind of count its opinion a little bit less, okay? Anytime we see like a 0.2, we're going to weight that more, okay? So, okay, so I don't know if it's still like this, but let's say you were trapped within one department or one segment of the university, okay? And different majors have different, say, gender ratios, okay? And so overall, UCLA, I think it's approximately like a 55-45 female-male split over the entire university, approximately. But some departments are perhaps closer to 80-20, okay, one gender or another, all right? And so it would be kind of like if you had to conduct a survey, okay, and you wanted to kind of get something representative of the entire UCLA campus, but you are like, wherever you're sampling, you're getting kind of the wrong, gender split or gender ratio. Basically, if you wanted to try to kind of compensate for that, okay, whichever group you are oversampling, you're going to kind of have to weight those opinions down a little bit less and average them down. And then the group that you're kind of undersampling, anytime you get, someone's opinion there, you have to kind of inflate, right? And basically, you say, okay, well, you're going to count for 3 people rather than 1 person. And then all of these people that we're getting too many of, you're going to say, okay, each of your opinions or whatever is going to kind of get averaged down. And that's kind of basically what we're doing. We're going to just say, when I'm generating my values, okay, I'm generating them from the red distribution. In the red distribution, we know we're getting too many values around here. So every time I get a value around here, we got to weight those down, okay? Anytime I get a value over here, we got to inflate those, all right? Because the true distribution should look like the blue one. So that's basically what we're going to do, okay? So when we do importance sampling, the mean of F, okay, the mean of the blue distribution is around 0.33. The mean of the red distribution is around 0.625, the average there, okay? And it says, so this is just kind of a silly thing, but let's say I didn't know what the mean of F is, and I want to estimate it via Monte Carlo, okay? If I'm able to sample directly from F, it's easy, right? I would just generate a whole bunch of values from F, okay? And then take the mean, okay? And we would expect that mean to be around 0.33, okay? But we're gonna say, our computer, for whatever reason, is not able to generate values from F, but is only able to generate values from G. So if I take a whole bunch of values generated from G, 100,000 values generated from G, and then I take the mean of all of those things, naturally I'm gonna get a mean close to the mean of G, right? So if here's 100,000 values, from G. G is the beta distribution with shape parameters 5 and 3. And when I take the mean of those values, I get a mean of 0.625. Okay, 0.6251737, which is close to the mean of G, which theoretically is going to be 0.625. Okay, but what I'm going to do is I'm going to apply a weight. Okay, I'm going to apply each of these observations, all 100,000 of these observations that drawn from the beta distribution. I'm going to apply this importance weight, which is going to be the PDF of F divided by the PDF G. Okay, so again, I'm going to get too many values that are close to 0.27, not enough values that are close to 0.2. So my solution is going to be to weigh these appropriately. When I draw a value that's close to 0.7, okay, the PDF of F is a lot lower than the PDF of G, okay? So around 0.7, F is lower than G. So this importance weight is going to be much less than 1, okay? On the other hand, when I draw values close to 0.2, the PDF of F is much higher than the PDF of G, and so my weight is going to be much greater, okay? So I'm going to weight those values much more heavily. G rarely produces a value near 0.2, so when I get one, we have to make it count. We're going to put a weight greater than 1, okay? So here my weights are going to basically be the PDF of the desired distribution. PDF is, my shape parameters are 2 and 4, okay, because that's what I want, beta 2 and 4. So I'm going to take the beta distribution with shape parameters 2 and 4, and I'm going to divide by the beta distribution, the PDF of that, with shape parameters 5 and 3. So this is going to be my vector of weights, okay? And so, this is vectorized. So each x, I've got 100,000 of these values, and I'm going to just basically do the PDF of F divided by the PDF of G, okay? And then so my vector of weights, I've got 100,000 of these things. Then I'm going to multiply all of the values of x that I have by their weights, and then I take the mean. And when I get that, I get a value pretty close to the actual value. So the true value is 0.3333, 1/3, and my estimate is 0.33288, okay? So not 100% accurate, but we're never going for 100% accurate. We're going for an estimate. And so we can see that by weighting these, we're getting a reasonable estimate, okay? And again, the PDF of the support of F has to be contained entirely within the support of G, and you can see that if it's not, then you're going to run into a situation where this is going to be 0 in the denominator, and then your whole thing blows up. Okay, so just to kind of show that it's not a trick, if I plot a histogram of X, you can see the histogram of X indeed aligns with the red distribution and not the blue one, okay? But indeed, if you just kind of take all of those X values and you apply them by this weight factor W, the mean of all of those weighted values is closer to the mean of F, okay? It's close to the mean of F, so that's what we have. Okay, so we can revise our algorithm just by using this importance weights. We're going to generate X from our distribution G, and then we're going to compute all of these weights, which is just the PDF of F divided by the PDF of G, and we have all of the weights, and then we're going to just say the expected value of H of X is going to just be the expected value of H times this weighting factor, okay? And again, the kind of key thing in the notation is we change this letter F to G, okay, indicating that the random variable X here is defined by the PDF G, whereas the random variable X here is defined by the PDF F, okay, to kind of denote that the PDF, or the random distribution that's generating these random values, has changed. This little subscript has gone from F to G, and we're going to say, okay, the expected value of this thing is that, and then we're going to estimate it by calculating H applied to each of the random values multiplied by the weight applied to each of the random values. All right, so let's try another example, okay? So here we're gonna try look at what's called the folded normal distribution. This is what you would get if you took the absolute values drawn from the normal distribution. So here's your normal distribution, and then what we're going to do, if this is if the center's at 0, so this generates z. Z comes from there. Basically we're going to just take the absolute values. Okay. And so now we get this. Okay. The total area is 1. The total area over here also has to be 1, so this is going to be twice as tall. It's going to be twice as tall. So the PDF of the folded normal is twice as tall as the regular PDF, but it exists only for positive values of x. So here's the PDF of the standard normal, and I'm going to just multiply it by 2, okay? And so you get this, all right? And so the support of x is 0 to infinity, right? And the question is, what is the mean of this distribution? Okay, what is going to be the expected value of f of x? All right, and so that's what we want. Okay, so here I just want to know what's the expected value of the random variable directly. So my h of x is just the value itself. I don't need to apply any kind of function to it. We'll just do that. Okay. And again, this is not too hard to do in real life, because in real life we can generate from the normal distribution, and then we can just take the absolute values and then calculate the mean. But again, we're gonna do importance sampling here. Okay. All right. So again, technically we could just generate values from the normal distribution ourselves. So here I'm going to generate 1,000,000 values from the normal distribution, and then I'm going to take the absolute value here, and then the mean of the absolute value is 0.79738812. Okay, we're going to do that. All right, but we're going to pretend we can't do this. So what do we do instead? Okay, so what we can do is we can generate values from, so this is the desired f of x. And instead, we're going to have, this is the exponential distribution, okay? And so the exponential is lambda e to the negative lambda x, right? And so here we'll, because this thing, we got negative x squared over, over 2 there, we'll pick we'll just pick a lambda of 2, okay? So my PDF is going to be 2e to the negative 2x, okay? And the support of both is going to be 0 to infinity, right? So the support of both of these things goes from 0 to infinity. And we are able to generate values from the exponential distribution in R using R exponential. And in the next week we'll learn how to generate random values ourselves, but here we can do this. Okay, so this is what we will do, is we're going to generate a whole bunch of values from the exponential distribution with lambda equal to 2. And then we're going to compute these weights. The weights is going to basically be the PDF of the f, okay? So this is the PDF of the folded normal, and we're going to divide by the PDF of g, which is just 2 times e to the negative 2x, okay? And we can do this by just kind of asking R to use the d norm. D norm is going to give me the normal density, and then d exponential will give me the exponential density. And again, this one has the d norm is twice as tall, so this is what we get. Okay? So R can calculate these things for me. I mean, I could do them myself, but why why do it yourself when R can do it for you? All right. And then we will calculate this across all of our values. All right, let me give you your next answer. Next answer is C. C as in cat. C as in cat is your next answer. Okay, so we'll try this out. I'm going to generate 1,000,000 values from the exponential distribution. So that's going to give me x. I'm going to calculate my weights. 2 times d norm of x divided by d exponential of x, rate parameter 2. Okay. My mean is, we're going to calculate all of the random values of x multiplied by the weights w. And then we get the mean to be 0.7976598. Okay. How does that compare to when we were able to generate values from the normal distribution directly and take the absolute values? It compares favorably. All right, so here, this is actually generating random normal values, taking the absolute value and calculating the mean there. And then theoretically, what is going to be the mean of that folded normal distribution would be the square root of 2 divided by pi. Okay, and that gives me this. Okay, so we're all accurate to around three decimal places. Okay, so it feels okay. All right. Again, Monte Carlo estimates. We're getting something, in the ballpark of what we want. Okay, after generating 1,000,000 values. So all to say, this importance sampling stuff, it works. Okay. This is, if you look at the folded normal, okay, you get the blue distribution. All right. If you take the exponential, you get the red distribution. Okay. And so basically, the decay on the exponential distribution is a lot faster. So the exponential distribution generates values close to 0 far more frequently. So I guess these two together look like that. Okay. So the exponential distribution generates values a lot more, and so what we're seeing, okay, the exponentials in red, the folded normals in blue, and then the ratio of basically the red line, the blue line, f divided by g is this black line here. Okay, there is the weight is in black. Okay, and so what we see is that over here, when we're generating values close to 0, we're weighting our values to be less than 1. When the red and where the red and the blue line meet, okay, so values at 0.5, that's where the exponential distribution is producing random values at the same rate as the folded normal distribution. Okay, so that weight there is equal to 1. Okay. And then over here, as in the normal distribution, okay, the normal distribution produces values between, say, 1, 2, 2.5, a lot more frequently than what the exponential distribution produces. So we have to weight those a lot heavier, okay? So, values around 2, okay, according to the exponential distribution, those values don't appear very often, but the normal distribution actually kind of generates values around 2, not super frequently, but a lot more than what the exponential distribution would. So whenever we get those, we weight those 3 times as heavy, and then it starts to drop back down until around 3.5, where the normal distribution, decays a lot faster than the exponential distribution. Okay, so exponential distribution. So the normal distribution, we think 68% between 1 and -1, 95% between 2 and -2. All right. The exponential distribution says, we don't really get values between 1 and 2 very often. Okay. both of these things say we rarely get values over 3.5, okay, or values over 4, okay? But the exponential distribution is a lot more likely to produce a value over 4 than the normal distribution is, okay? So the normal distribution like almost never produces values over 4. And the exponential distribution rarely produces values over 4, but it produces them a lot more frequently than what the normal distribution would, right? So I mean, that's probability distributions. And as much as like we study statistics and stuff, I think like people just don't have a very great understanding of randomness and probability, right? Like if you say something that has an 80% chance of happening, like you feel like, oh, that's a pretty good bet. But like that 20% happens 20% of the time. And I think for a lot of people, like 20% is actually a lot more than what they might expect, right? Like, because 80% you feel like, oh, okay, like that, we got this in the bag, but no. So, okay. Okay, so here is, what do we do for something like this, okay? What if we want to estimate the probability that z from a standard normal distribution is over the value 4.5? Okay. So the true value, okay, is on the order of what? 3 times 10 to the minus 6, okay? 3 times 10 to the minus 6. Now, if we wanted to, we could have tried this doing just regular old Monte Carlo integration, okay? Or if we go back to Wednesday's lecture, the way we would estimate this quantity is I would just sit at my computer and I'd say, computer, generate a whole bunch of random normal values. Okay, so I would say like generate 1 million random normal values. And then I'm going to say, okay, out of those million values that you generated, how many of those values were greater than 4.5? Okay, and then the computer says, oh, I generated 1 million values and two of them were greater than 4.5. So my Monte Carlo estimate at that moment in time would just be 2 times 10 to the minus 6, okay? Which is, I mean, at least it's on the same magnitude, order of magnitude here, but it's not a great estimate, okay? So again, because z being greater than 4.5 is so rare, it just happened 2 times in a million. This is not a really great estimate of the true probability of around 3.4 times in a million. So, so what we can do is we can improve our accuracy by just kind of, one is we could just sample more values, okay? We could say like, all right, instead of 1 million, generate 10 million, and I would just sit around in front of my computer even longer. Or I could use importance sampling, okay? All right, and so what I can do is, so, you know, what our goal, again, so here's my normal distribution, and here I'm just coming all the way out to this tail of like 4.5 and greater. So it's just this tiny, it's just this, you know, if we zoomed in here, we've got some kind of tail that looks like this, right? And this is you know, 4.5. And what I can also do is I could just take kind of another exponential distribution that just starts at say 4.5. Okay, and so like the exponential distribution has like this memoryless property, right? That like because it's kind of like, what's the expected value of a brand new light bulb? Because like, I don't know, is that the classic example for when you use the exponential distribution is like, how long do you expect a light bulb to last, right? So when you buy a brand new light bulb, you might say like, okay, we expect this thing to last 1,000 hours, okay, from now. But then it has this memoryless property where it's like, okay, the light bulb has been on for 200 hours. How many more hours can I expect it to last? And the answer is I can expect it to last another 1,000 hours, right? And just kind of like every day you sit and you say, well, how much longer can I expect it to last? And it's like, okay, well, if it's survived up to this point, our expected value is still like another 1,000 hours, which seems so crazy, but that's the property of the exponential distribution. Okay, so anyway, we could take an exponential distribution and just kind of slide it down. Okay, that begins at 4.5. All right, we know that the PDF must integrate to 1, so we can just say, all right, well, I'm going to just, so the idea here being, so if this is kind of the exponential distribution, and we're going to say, so normally it starts at 0, but we're going to start at 4.5, okay? And we want to just kind of do this. Basically, all I'm going to do is I'm going to just take this thing, multiply it by some kind of constant. So we're going to just kind of inflate it like this, okay? So that the thing that starts at 4.5 will integrate to 1, okay? So that's all I'm saying, right? Is we're just going to take, we're going to take this quantity, multiply it by some constant. What should that constant be? Okay, so I'm going to just take the exponential distribution is e to the minus x. We're going to just kind of divide it by whatever constant this is. And it turns out, well, you just kind of slide the thing over, 4.5. Okay, so this is the constant by which you're going to multiply, all right? And so that's equal to e to the minus x over minus 4.5. Okay, so this is going to be the g of x. I'm going to generate values from the exponential distribution. I'm just going to add 4.5 to everything. So my weights will be the normal PDF divided by this exponential PDF where I've kind of slid everything over by 4.5. All right, and then I still have the indicator function. I'm going to do a 1 if it's greater than 4.5, 0 if it's less than 4.5, okay? And here, all of my values are going to be greater than 4.5 because I'm going to just generate values from the exponential distribution and I'm going to add 4.5, okay? So we're going to just generate random values from the exponential distribution and add 4.5 to all of them because that's kind of how the exponential distribution works, right? So doing that, the resulting distribution is exactly equal to an exponential distribution that generates values starting at 4.5, and that's because of, again, the memoryless property of the exponential distribution. And you can check out the math behind it, but basically this applies and this works, okay? And so therefore, if all of the values that I generate from the exponential distribution are greater than 4.5, then my indicator function, h of x, is going to be 1 for all of my generated values. So I don't have any values to kind of throw away, okay? So now that I have this, I just have to kind of weight everything. And so we'll do that, okay? So the expected value here is going to be calculated like this, all right? So I'm going to just generate 1,000,000 values from the exponential distribution, and I'm going to add 4.5 to all of them. And then we're going to calculate the PDF, all right? So we're going to plug in each of these values into the normal PDF. And so we're going to get really, really, really tiny values because we're all the way out here, okay? But all of them get weighted in accordance to my exponential thing, okay? We're going to do d exponential of this. And so all of these values, they get kind of weighted, really small, right? And then my mean, okay, my function h is just 1 for everything, so it's a little unnecessary to do this, but we're going to do the mean of h times w. And we get 3.390826, okay? Which is pretty close, or a lot closer to the theoretic value of 3.397, okay? Versus the standard Monte Carlo approach, I just sat around and I generated 1,000,000 values and I got 2.2 out of 1,000,000, right? But the p-norm is what, 3.397, and we're getting something pretty close to that, 3.39. Okay, so again, with 1,000,000 values, you get around three significant figures of precision, and that's, we say, well, that's pretty decent. Okay, And so, yeah, you could use this importance sampling to kind of get down to extreme values or wherever it might be. Okay, we'll wrap things up here. And, I'll go ahead and I will give the view quiz answer also to the video. Third view quiz answer to everybody. Last answer is D. D as in dog. D as in dog. Okay? All right, so we'll end there. Have a great weekend. Homework 2 has been posted. You can start to take a look, and you can actually, I think you have everything you need to start working on it. So good luck with that. Have a great weekend, and we'll see you Monday.